Hey everyone. Right now what we have, we've been studying this notion of divisibility and factorization. We have a couple of competing notions of what we might think of as prime, right? We have irreducible and we have prime. And so we want to just kind of tie up some loose ends now. And so this was an observation from a couple of lectures ago. So it was observation 3, so let's just say recall. And remember, all of this happens in an integral domain. So in an integral domain, if let's say in an integral domain D, if little p in capital D is prime, then P is irreducible. Right? So prime implies irreducibility. This was observation 3. I don't remember. It was like about 2 lectures ago, so you should have this in your notes. Now, one thing that we're aware of, so remember, irreducibility, the definition of irreducible, is essentially what we use for the definition of prime when we're working with integers. And then the definition of prime that we're working with now in an arbitrary integral domain is really what we would call Euclid's lemma when we're working in in the integers. And it turns out when you're working in the integers, either one of those is actually a suitable definition of a prime number, right? They're equivalent, right? If you define prime the way we normally do, you can prove Euclid's lemma, and then Euclid's lemma also implies prime, right? So they're equivalent. And there's a reason for that, and that is going to be this theorem right here. So this is theorem 45.5. So let's let D be a principal ideal domain. If little d in capital D is irreducible, then D is prime. So in a principal ideal domain, right, we already know that prime implies irreducible in general. And now in a PID, we have the converse, right? Irreducibility implies prime. So that means that in a PID, the notions of irreducibility and prime are exactly the same, right? Okay, so for the proof, let's choose an irreducible element. So let's say assume little d in capital D is irreducible. And so now what I want to do is show that D is prime. So I'm going to say suppose that D divides some product. So let's say and suppose that D divides A times B for some little a and b in capital D. What we need to do is show that D divides A or D divides B. Now, here's what we know, what we proved last time, so we can say it like this. So since the ideal generated by D is maximal, this was, I guess it was our last, was it, 45.5, right? We proved that in a principal ideal domain, irreducibility of an element is equivalent to the ideal being generated being maximal. So since D is maximal, this is theorem 45.4. We have that that the ideal generated by D is prime. Right, this was, I think, it was a corollary, right? We know that maximal implies prime. That's corollary 27.6. Now, okay, so D divides A times B. That means that AB is in the ideal generated by D, right? So since AB is in the ideal generated by D, we have A is an element of the ideal generated by D, or B is an element of the ideal generated by D. Therefore, D divides A, or D divides B. That's just what it means to live in the ideal generated by D. And so, D is prime. So, it's actually not a difficult proof, right? It relied on our previous theorem right here, right? 45.4, the fact that anytime in a PID, if we have an irreducible element, the corresponding ideal is maximal. So, in fact, that's the end of the proof, but now let's actually put it down. So what we have now is in a PID, irreducibility is equivalent to prime. So let's say combining 45.5 with observation 3, we have that, let's just write it like this, prime if and only if irreducible, why can't I spell it now? Irreducible in a PID. Right? So that tells us then that, when we're talking about the integers, it's okay. I mean, traditionally it was already known the word prime came before the word irreducible. But now, noticing how we define the two, it really doesn't matter, right? The integers is a PID. The integers is a PID. And so prime and irreducible are interchangeable in a sense. Now one thing... what was this? This was, let me just look, I gotta look up the number of the theorem. Oh, right, sorry. So here's another, let's just call this, I guess, observation. So if capital D is an irreducible, if capital D is a PID and little d in capital D is an irreducible, and I don't like the sentence already. If D is a PID, let's say, let's put a comma here. Little d is an irreducible, and D divides a product A1 up through A sub n, then D divides AI for some 1 less than or equal to I less than or equal to n. So that's sort of generalizing the notion of prime, right? We know irreducibles are primes in PIDs, right? So if D divides a product of two elements, then it has to divide one of the other. Basically, by induction, then, if D divides a product like this, then it has to divide one of them. All right, so now we're ready for the big result. So this will be theorem 45.6. If D is a PID, then D is a UFD. In our last lecture, we got part of this proved, right? We have the factorization part, we just don't have the uniqueness yet. So we're going to do the uniqueness now. So for the proof, so we're going to take a non-zero, non-unit element. So let's let little d in capital D star, so D is non-zero, be a non-unit. So now what we know is that D can be expressed as a product of irreducibles. So by theorem 45.3, there exist irreducibles P1 up through P sub M, I don't know why, for some reason I use M, in capital D such that little d equals the product P1 up through P sub N, right? So we know that a factorization exists. Now we need to show that it's unique up to reordering and sliding units around. So up to reordering and associates. All right. So now we're going to do the uniqueness. So suppose there exist irreducibles Q1 up through Q sub N, N in D, such that D equals the product Q1 up through Q sub N. And now this proof is going to look very much like the proof that we did for polynomials. In fact, it's essentially the same proof. So then we have P1 times product P2 up through P sub M equal to Q1 up through Q sub N. And so what that tells us is that P1 divides the product Q1 through Qn. So now we can assume up to, just by reordering things, that P1 divides Q1. All right, so since P1 is irreducible, we know it divides one of them, so we can assume without loss of generality that P1 divides Q1. Okay, so what does that mean? It means that P1, well, Q1 is equal to P1 times A1, I think I use here, yeah. Let's say, so Q1 is equal to P1 A1 for some A1 in D. But wait a minute. Let me think here. Q1 is irreducible. P1 is not a unit. That means A1 has to be a unit. All right, so since Q1, right, is irreducible, which means that anytime you factor it, one of the two has to be a unit. We know that P1, because it's an irreducible, is not a unit. So since Q1 is irreducible and P1 is not a unit, we conclude that A1 is a unit. All right, so what does that tell us then? It tells us that P1 and Q1 are associates. Thus, P1 and Q1 are associates. All right, so now in this equation right here, we could substitute for Q1, right? We'll have Q1 equal to P1 times A1 and then cancel the P1s. So now we have P1 dot 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 Pm equals P1 A1 Q2 up through Qn. And so, cancel the P1s and we get P2 dot 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 Pm equals Q2 dot 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 Qn. And then you can just repeat this process, right? We'll be able to show that up to ordering P2 and Q2 are associates. Cancel that off. And so, now what we're going to get, right? So let's repeat this process. So repeating this process, we have, two possibilities depending on which one's bigger. Either M is bigger or N is bigger. So we have, let's see, if N is bigger, then eventually we'll cancel off all the P's. So we'll have, let's write it up here. So if N is bigger, we cancel off all the P's, and so we'll get 1 equals, cancel off all the P's, so we'll have cancel M of them, so we'll have A1, A2 dot 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 up to AM, and then we'll have QM plus 1 dot 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 QN. This is in the case that M is less than or equal to N. That I run right? Yeah. Or if we canceled off all the Q's, we would have P. Or if we cancel off when we run out of Q's, then we'll have just A's, A1 through AM, I think. So P. What's my index here? Oh, P sub N plus 1. P sub N plus 1 dot 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 to P sub M equal to, and then we'll just have A1 up through AN over here. This would be in the case that M is greater than or equal to N. So in the first case, what would this tell us? Well, multiply all those A's over, and then we have a unit over here equal to a product of non-units over here, right? The only way that can happen is if really M was equal to N, right? So in the first case, well, actually, this is true in both cases. So in each case, we have a product of irreducibles equal to a unit. So in each case, we have product of irreducibles equal to a unit unless which is impossible. Well, okay, so unless m is equal to n. Right? If m is equal to n, then we'd have perfect cancellation, and in the end, we would have some product of units equal to 1, which is fine. Okay, so since the product of irreducibles cannot be a unit, that tells us that m equals m, so therefore m equals n, and so now we have completed the proof. Every non-unit, non-zero element in a PID can be expressed as a product of irreducibles in essentially a unique way. Right? Anytime if you have some other expression. Oh, and you know what? I just realized right there that one should have been an n. Oops. So anytime if you have some expression, or let's say two different expressions, two supposedly different, then the number of irreducibles in any factorization of our element D has to be the same, and E has to equal n, and one by one, the elements in the factorization, or one of the factorizations, have to be associates of the elements in the other. Okay. As a quick consequence of this, so this would be corollary 45.7. Well, okay, so this corollary has a name. It's called the fundamental theorem of arithmetic. And in our more advanced language now, what we can say, or the way we can state the fundamental theorem of arithmetic, is that Z is a unique factorization domain. And the proof, this is just from an earlier example, we showed that Z is a PID. Right, so the proof in an earlier example, we showed that Z is a PID. Well, that's kind of exciting, right? I think you've been told, I mean, maybe in number theory, I don't know what people do in number theory, but maybe you prove that in number theory. But here, we have a nice proof. It took a lot of machinery to build it up, but now there's essentially nothing to do, right? We know that Z is a principal ideal domain, and we know that every principal ideal domain is a UFD, a unique factorization domain. Okay. Well, I don't think I want to start a new. Oh, never mind. No. I thought for a second we were done with the chapter. I have one more thing that I want to talk about, and then we're going to start a new chapter. And so, let me state the theorem here. So this is going to be 45.8. And it goes like this. So if D is a UFD, then D bracket X is a UFD. That's maybe not obvious. And this is one of the cases where I'm not going to go through every step. It actually takes quite a bit of work to prove this one. I just want to sketch the proof. So, I'm going to sort of write out the steps, and it does really take some work to show this. Okay, so if we've got our ring of coefficients, we're assuming is a UFD, and so the first step, we have to define what a greatest common divisor is in an arbitrary UFD, right? We know what it means for the integers, but that's as far as we've defined it. So if a, say 1 up through a sub m are elements of D star, so non-zero elements, then D is a GCD of A1 up through AM if, okay, so now here's the problem, or here, with the integers, we have a notion of larger. But in an arbitrary ring, right, or arbitrary, you have D, there may or may not be a notion of order, right, where we can say that this element is bigger than this other element. And so we need to find greatest common divisor without the luxury of necessarily having an order on our ring. And so it goes like this. If D, well, divides AI for each one less than or equal to I less than or equal to N, or M, obviously, right? So D needs to divide each one. And then we say and if C divides every one of them, so if C divides AI for each one less than or equal to I less than or equal to N, then C divides D. So there's our notion of being bigger, right? If you are divisible, right? If C divides D, then we think of D as larger than C. One thing to be aware of, any two GCDs are associated. So notice, I did not say the GCD. Right? I said and, or a GCD. So, so let's just say note, any two GCDs are associates. Right, so they just differ by a unit. Okay, so there's step one, is we need this notion of GCD. The second step, and this is not really a step, but once again it's a definition. So a polynomial f of x in D, where am I? Oh yeah. In D bracket x is primitive, right? So we need to generalize this idea of primitive. So a polynomial is primitive if the GCD of the coefficients, if a, let me say it better. If 1 is a GCD, so if 1 is a GCD of the coefficients of f of x. Okay, so that matches the way we defined it for integers, or polynomials with integer coefficients. The third step is that there is a generalized Gauss lemma. So in fact, let's call it that. So generalized Gauss lemma. So remember, the product of primitive polynomials is primitive. So a product, or in D bracket x, a product of primitive polynomials is primitive. Remember, we used this fact to show that if you could factor over q, then you could factor over z. Okay, so now so the next thing, and this is, you need to prove this, and And it's going to be sort of a generalization of what we used Gauss's lemma before. So let's let F be the field of quotients of D. And so it turns out then, if f of x in D bracket, yeah, okay, yeah, so if f of x in D bracket x is irreducible over D, then f of x is irreducible over f, right? So we prove this in the case of an integer polynomial, right? If it's irreducible over the integers, then it's irreducible over Q, which is the field of quotients for the integers, right? So you can generalize the proof that we did in that setting. So, so it follows that that what? A polynomial in D bracket x factors over D if and only if it factors over f. Okay, so now use the fact that f bracket x is a PID, hence a UFD. Right? So that's the punchline right there. Take a polynomial in D bracket x, view it living in F bracket x, factor it, and then conclude, oh, the factorization that you would have done, so factor it in its unique way over F bracket x, right? Express it in its unique way as a product of irreducibles in F bracket x, and then recognize that, oh, you could have only, since you were able, or however you did it here, is how you would have done it here, and that is unique. Right? So there's some details to fill in here. This is just a sketch of the proof. Right? You're not going to be held responsible for filling in the details at all. But as a sort of quick corollary, a consequence, Z bracket x is a UFD. Why is that? Because we know that its ring of coefficients Z is a UFD. Even though, so here's our example now. We know that Z bracket x is not a PID, right? So this shows, so this example shows that the converse to 45 point whatever 45.6 is false. Right? Z bracket x is a UFD, but not a PID. Okay? So we know PID implies UFD, not necessarily vice versa. Right? There's your example. Okay, that's a good place to stop. So we're going to start a new chapter next time. So we'll see you then.